First of all, I'd like to thank the organizers for organizing this very nice event. So this is kind of a talk, after lunch talk, where there's no calculations or anything, it's just some ideas. So it's easy to follow. So this is something I've been thinking for a long time, and it's still not written up anywhere. This is the chaos in popular culture is basically this. Butterfly fluttering its wings in Beijing causes a tornado in Kansas. So it could be anywhere, like even Bangalore, but this is the cartoon I found on internet. So now the basic idea is a very small effect causes some big effect. Okay, so this is what is this really true? This is the basic idea of the talk. Okay, so I just want to say how it was. This effect was discovered by Lorentz. So the good thing about giving a talk is that you read a lot about the history, and so this is what I found out yesterday. So Lorentz was a mathematician and a meteorologist trying to make simple models of the weather even around 1960s. So it was the beginning of modeling weather. And with his collaborators, Ellen Fetter and Margaret Hamilton. So actually, it turns out these are the people who actually wrote the code and all, but in the paper you never see them. So they used a simple computer to run weather simulations. So weather means basically, let's say, Navier-Stokes equation, but you reduce it down to very few set of equations, and then just simulate it on the computer. Okay, so they ran the simulation with some initial conditions for some time, and then they just wanted to run it again. So instead of starting from the same initial conditions, they took the initial conditions at some intermediate time, and then again ran the simulations. Okay, so now at that time, the way data was stored is you just print it out on a piece of paper, and they had when they print out, it's stored up to let's say 3 decimal places. For actual value might be 6 decimal places. Okay, so they used this data and then they ran the simulation again, and they found that the trajectory was completely different. Okay, so this is how. So even though you make an error in initial conditions which are after 3 decimal places, at long times the evolution of the weather is completely different. Okay, so this is. This difference is tiny, and the consensus. So at that time, people thought it should have no practical effect, but Lorentz discovered that small changes in initial conditions produces large changes in long-term outcome. And so this was published in this journal in '63. And okay, so this paper is really nice. One of the things he shows is what are known as attractors. So if, let's say there are just 3 degrees of freedom, and if you plot like what happens at long times, then they don't go into a periodic orbit, they don't go to a fixed point, they keep evolving like, non-periodically in some very strange, so it's called a strange attractor. Okay. So, yeah, so this is what the strange attractor that Lorentz discovered looked like. And you can also see another connection to the butterfly effect is that this attractor looks like a butterfly. There's also some, I think, series of movies called The Butterfly Effect. I haven't seen, but I think it's motivated, or at least sort of connected to the butterfly effect. Okay, so it's a very popular thing, the butterfly effect and chaos. Okay, so the precise definition of chaos is this. I mean, let's say you have some dynamical system which has n degrees of freedom, and these are some first order differential equations. Which are typically should be nonlinear. And if you start from 2 different initial conditions, let's say ZA0 and ZB0, which is differ by a very small amount, then you find after some time they start diverging, right? Okay, so for the precise definition, you also need that the initial difference should actually go to 0. It should be an infinitesimal difference. So, I mean, this is valid even for a system where, let's say, the phase space is actually just between the unity interval 0 to 1. Okay, so even there you can have exponential divergence because the initial difference is very small. Okay, so this is the precise definition. Now, the basic question that we are asking is, does this imply that we cannot make any reliable predictions? Okay, so small changes in initial conditions lead to huge changes in trajectories of systems. So trajectories means this n degrees of freedom it could be n positions of n particles and n momenta. So these are the see some 6n-dimensional phase space. There's a trajectory, and if you look at another slightly different trajectory, they follow completely different paths. Okay, so now the popular notion is that this kind of, because of chaos, this affects our ability to predict evolution of systems such as, let's say, weather, climate, planetary motion. I mean, so this is also one area where the idea of chaos started from the work of Poincaré and all. Even stock market prices, disease evolution, ecosystems. In fact, Ashik talked about this today morning. And let's say even water flowing through a tap. Okay, so these are all systems with many degrees of freedom, non-linear systems. Can we actually make predictions? Because I mean, it seems it's difficult, right? Okay, so basically what I'll argue is that this interpretation of chaos, so there's chaos in the microscopic dynamics, but on macroscopic phenomena, it doesn't have any effect. Okay, this is what I'll try to argue. And basically, the butterfly effect of chaos theory does not lead to any loss of predictability in macroscopic systems. Basically, statistical averaging restores predictability. And the main thing I'll argue is that the fact that linear response theory and hydrodynamic theory are valid, that already shows that chaos is kind of irrelevant. Okay, so let me just say what is linear response theory. Okay, so linear response theory is basically like if I do a small perturbation here, like if I, for example, I hit this table out here, I'll get a response here, and that will be small. Okay, so that's just linear response theory. I mean, so mathematically, the derivation of the theory is you take a Hamiltonian system, and then you perturb it in some way, and then what you look at some observable. And you find that the observable changes from its equilibrium value by a small amount. And the small amount depends on the perturbation in a linear way. Okay, so this is the response, and this is the perturbation, and this is the response function. Okay, so it's just a linear relation. That's the main idea. And this response function can be calculated from, let's say, just equilibrium statistical physics by computing various correlation functions. Okay, so this is one thing which already says that whatever very complicated system I have, if I wave my hands here, I mean, there's only going to be a small effect at the end of the room, right? I mean, you can't have a huge macroscopic effect. Okay, so this is the basic argument. Okay, I don't have anything more detailed calculation to say why chaos is irrelevant for macroscopic response. Okay, so so there's an interesting paper by Van Kampen in 1971 where he was objecting against so linear response theory is very old. I mean, started with work of Kubo and so on. So there was this paper by Van Kampen in 71 where he said that, I mean, the linear response theory cannot be correct because, I mean, we know from chaos that small perturbations have a large effect. Okay, so how come linear response theory, which is derived assuming linearity of a microscopic response, why does it work? Okay, so he pointed out that the standard derivation of linear response theory seems to rest on microscopic linearity. However, the presence of chaos in typical interacting systems would then imply that responses are linear only on extremely short time scales. At long time scales, obviously the derivation would break down. Okay, so now it's clear actually that the predictions from we all know that linear response theory works. I mean, entire condensed matter physics is based on linear response theory. And it's obviously true for even when the microscopic dynamics is chaotic. Okay, so the main point is that the macroscopic linearity of responses that we observe in macroscopic systems is a result of statistical averaging and coarse graining. Okay, so when we observe things, we are not observing a molecule. We observe, let's say, a bunch of molecules. So there's some coarse graining going on. Okay, so individual molecules, of course, might have, like, if you start from different initial conditions, individual molecules can be in very different positions and so on. But once you coarse grain, the observable that you actually measure, that won't show the effect of all this chaos. Okay, so the process of coarse graining or ensemble averaging makes chaos irrelevant and restores our ability to predict. How much time? 3 minutes, 2.5 minutes. Okay. Okay, so the other example is hydrodynamics. So basically, I mean, like you can a coarse-grained view of matter is based on hydrodynamics, where instead of looking at all the molecules in a room, we just look at a few macroscopic fields like the density field, velocity field, and temperature field. Right? This is what like people talking about fluids have been discussing. And you don't care about what the molecules are doing, okay? But it's the same system, but you can have a coarse-grained description. So now hydrodynamics is based on the idea of macroscopic typicality, which says that a given specification of the macrostate actually corresponds to a large number of possible microstates. Okay, so you can arrange the fluid molecules in number of ways, but it will give you the same. It will give you the same density profile, same temperature profile, and same velocity profile. Okay, but microscopically they might look very different. But we know that equations of hydrodynamics are deterministic. So even though microscopic configurations can be completely different, the macroscopic evolution that you observe will be identical. So this is what I'm saying here. Each microstate has a very different trajectory in the microsphere space, microscopic phase space, but this does not show up in the evolution of the macroscopic fields. They will follow, the macroscopic fields follow a unique trajectory. Okay, so this I think I can skip. This is just going from the Newton's equations to the coarse-grained description. Okay, so I'll just give another example of some problem that I am interested in. It's called the blast problem, and it's the basically problem of the which started with this Trinity explosion, where you basically release a huge amount of energy in a very concentrated space and see how it evolves. Okay, so now this you can imagine is the most chaotic situation, right? I mean, it's a bomb blast, but I mean, this problem was studied by people like Taylor, von Neumann, and so on. And using the hydrodynamic equations, you can actually predict exactly how this, for example, this bomb is the profile of the bomb evolves. Okay, I mean you can predict the time dependence, you can predict the prefactor, everything very accurately. Okay, so even though it's an extremely chaotic system, it doesn't matter. Eventually, just using coarse-grained description, you can have a very deterministic prediction. You can predict what's the temperature at the core of the blast and so on. Okay, so I also did some search about like have other people said anything about this problem. Okay, and I found out this book called Truth or Beauty by this person called David Orell, and he seems to have a similar idea as what I am saying. So I just end with this. Yeah. So coming as I did from background working on engineering projects, I knew that mathematical models are prone to error even in highly controlled environments. Okay, so my research indicated that the butterfly effect was a myth. When butterflies flap their wings, the perturbation to the atmosphere is rapidly damped out. So you can try this out of this obvious, right? So the fact that this undemonstrated theory has been evoked for decades as the default explanation for prediction error in many fields tells us more about the sociology of science and the attraction of a pretty idea than it does about reality. The real cause of forecast inaccuracy was something much less aesthetically and professionally appealing model error. Okay, so it might be just we are not. I mean, something was out there in the atmosphere pushing forecast astray, and modelers didn't know what it was. Okay, so it's not because of deterministic chaos. The reason we can't predict is for other reasons. Okay, so maybe I'll stop here.
Questions, please. Yes. Yeah, go ahead.
The first part of your talk, what about, say, sitting at a critical point and perturbing slightly in a relevant parameter so that you have a small perturbations and that really requires a long length scale for the effect of that perturbation to show up?
You're saying critical point in like a phase transition?
Yeah.
Yeah, there might be situations where a small perturbation you're saying can have a big effect in a macroscopic system.
Right.
Yeah, there might be very special situations, but not generically.
Okay, so I mean, then sort of semi-rigorous point. Then this sentence about butterfly effect may be a statement about particular mathematical situations and not really the context that it is sociologically accepted.
Right, yeah. No, it's a very precise definition, and but its effect is not like as is people
In this
take it out.
sociological setting of weather
Yeah.
and things like that, which I don't know much about.
No, I'm saying it doesn't affect predictability in typical situations, like where like it doesn't affect the fact that we can't predict weather is not because of chaos.
Right. So in that sense, the underlying chaos really determines the statistical ensemble in which over which you're averaging to determine these quantities. Isn't that true?
No, see, but like if you take a, I mean, if you take a typical, let's say, macroscopic phenomena, let's say gas flowing in air, like, I mean, as long as like you are measuring some, like you are given the density, the macroscopic fields, let's say density, temperature, and velocity fields, then I mean it doesn't matter too much what ensemble you are using. I mean, whether you're using microcanonical or the ensemble doesn't matter.
No. So, I mean, there are these three particular ensembles, but
Yeah.
the fact that temperature, etc., comes out to be good coarse-grained quantities,
Right,
that's in also some sense assumes some structure about the coarse graining, right?
Yeah, they are, because they are the conserved quantities, they are the slow fields. That's why they are important, right? They are I mean, that's why they are. I mean, they describe like local equilibrium and so on.
If may I interrupt?
Yeah, sorry.
Yeah, this. Yeah, any other question? Yes, Tithadi.
Okay, since this is about predictability, doesn't it matter as to what kind of observables you are trying to predict? I can imagine situations even in my macroscopic contexts where the observable of interest is not, not an average or not a linear function of the trajectories.
Right, yeah.
So in
Yeah,
that case, you will see the divergence of trajectories.
I mean, if you are, of course, like looking at a molecule, right? Then
No, not for
obviously
a molecule, but some property which, I mean, obviously I have something like entanglement in mind, but forgetting about that, I can think of observables which are not linear functions of the trajectories, which are not simple linear averages of the trajectories.
Like these are not typically linear property. I mean, as long as you do some coarse graining, like you are looking at not one molecule but a bunch of molecules in some small volume.
But but then you're assuming that the observable is that the coarse graining is allowed in some sense. You're basically saying that the coarse grained behavior is a good representation of the of your underlying physics. This may not be the case. So you are actually sort of using chaos as a crutch to make this statement, right? Because if you don't have chaos, then you don't have equivalence of ensembles. Equivalence of ensembles depends on ergodicity, which is one.
No, but you don't need chaos to get ergodicity.
You don't need chaos to get ergodicity, but you do need this whatever this thing is called, equal probability measure.
Right, yeah, but you don't need chaos.
So, thank you, Abhishek.